SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be lecture number 4 on our series on mechanical measurements. In the previous lecture, that is lecture number 3, we were looking at the question of propagation of errors, that is the propagation of the error from the measured primary quantities to the estimated value of the derived quantity. We have already derived the formula and we will resume from there. We will also give an example which will consider two different ways of solving a particular problem. Then subsequently, we will look at introduction to regression analysis. Regression analysis is the study of relationships between different measured quantities, and they may be either linear, non-linear and so on. So, we will be looking at the basic ideas between regression analysis, and then subsequently we will take up linear regression as a in a more detailed fashion, and if time permits, we will be actually solving a specific problem. So, towards the end of the last lecture, we actually derived a relationship which is rewritten here in this slide. So, we have a Q as a derived quantity, and AJs are the quantities which are primarily measured, and Q is estimated, and Q is a function of AJ from j equal to 1 to m. If the precision of each one of these measurements AJ is known, for example, sigma AJ gives you the standard deviation for each one of these measurements, then I form a product of the partial derivative Q with respect to AJ multiplied with sigma AJ. This is the first part. The partial derivative is nothing but the influence coefficient, and sigma AJ is the precision of the particular measurement. I add such terms and square them from j equal to 1 to m. This gives you the variance in the error of the measured value, estimated value of the quantity Q. So, what is happening here is that the error in the primary quantity which is measured, which is given by sigma AJ, is contributing a certain amount to the error in the quantity Q, and that is given by the influence coefficient multiplied by the precision of that particular measurement. So, sum of the squares, and this is just like taking the magnitude as a vector, or the use of the Pythagoras theorem, which gives you the sum of the squares is equal to squares of the hypotenuse. In this case, of course, we are extending this idea of Pythagoras theorem to several dimensions instead of just 2 dimensions which we normally use in geometry. So, with this background, let us take a look at a simple example. Example 3. In this case, we measure A, P and T. These are the 3 measured quantities, and the quantity m is estimated, and the formula which links the value of m to A, P and T is given by the formula here, m equal to A times P by root T. Let me just digress and just tell you what we are trying to do, what is this problem. In measuring fluid flow, sometimes we use a sonic orifice, and in that case the mass flow rate of the gas is given by some constant which is obtained by some kind of a calibration process multiplied by the stagnation pressure and the stagnation temperature upstream of the orifice. So, this is an example which is taken from fluid flow, and let us see what we are going to do. This further specification in this problem is as follows. The nominal values for A, P and T are given. A is 10, P is 20, T is 4.84. What I have done is I have chosen the values such that it is dimensionally homogeneous, and these values are just the numerical values. The standard errors in these quantities A, P and T are also specified. Sigma A is 0.1%, sigma in P is 0.2% and sigma T is 1%. We would like to specify an error bar on the derived quantity M, that is the thing we would like to do, and that I am going to work out on the board by what I call as method number 1. So, I will go to the board, and in fact this is the formula which we have written down, which was written down towards the end of the last lecture. So, I am just going to use this as the basis for solving the problem, and let us write down the formula which is given to us. M equal to A P by square root of T. If you remember, the value of M or the best value of M is what is determined by using the values of A, P and T which are specified in the problem, and therefore, I can calculate this value as A is 100, I think it is 10, not 100, P is 20 divided by square root of 4.84, this was specified in the problem, and this gives you a value of 90.91. I have just rounded up to 2 significant figures after the decimal point. And this is the value of M which is expected for the values of A and P and T which are given in the problem. Now, I have to find out the error. To determine the error, I have to find out what are the influence coefficient. So, I will call them as influence coefficient is Im Now, I will change it to IA. Influence coefficient for IA is nothing but dou M by dou A, which is simply given by P by square root T, and that will be 20 divided by square root of 4.84, and this value works out to be 9.091. And similarly, if I represent the influence coefficient due to P as IP, it will be dou M by dou P. So, when I am taking the partial derivative, all other things are kept as though they are constant. So, this will be A by root T ten divided by square root of 4.84, and this is 4.545. So, two influence coefficients are there. The third one is I subscript T dou M by dou T. This will be minus half A P by T to the power of 3 by 2, and I can substitute and obtain the value as minus 9.39. So, the three influence coefficients are available here, and the values of the errors or the standard deviation of the errors of the quantities A, P and T are specified as percentages, Therefore, I will first obtain the actual values. So, if you take sigma A is 0.1%, this will be 0.1 divided by 100 multiplied by 10. This is the actual value. So, this will give you 0.01 and sigma P is 0.2%, and that will give you 0.2 divided by 100 into the value of the parameter P, which is 20. That will give you 0.04, and sigma T will be 1%, that means 4.84 into 1 over 100 0.0484. So, once we have obtained all the sigmas, and if we go to the previous, we have obtained the influence coefficients, we can obtain using the error propagation formula sigma m squared will be the sum of three quantities I A times sigma A whole squared plus I P sigma P whole squared plus I T sigma T whole squared. If you want sigma m, all I have to do is to take a square root and put a plus or minus sign. And in fact, you can substitute the values which were obtained in the previous slide, and then I can just substitute here. I will leave it as an exercise for you to complete. It will give you 0.248. That is the value of sigma m squared. If you calculate sigma m, it will be square root of this, which will be plus or minus 0.498. I can also calculate the percentage value. For example, the value is m is given, and I have got the value of sigma m. So, sigma m in percent will be sigma m given above divided by m multiplied by 100, and this comes to about 0.55%. So, you see that the problem of propagation can be calculated in a mathematical fashion as we have done in this particular case. So, now I will go back to the presentation where we left it off. So, I will go to the next slide and discuss a different way of doing the same problem. So, let me just explain to you what we are trying to do. On the board, we have indicated how to work out in detail the several steps involved in the process. I have obtained the influence coefficients. I first obtained the value of the quantity m in this case, which corresponds to q in the general formula which we worked out earlier. Then we calculated the individual sigmas. From the percentages we calculated in terms of actual values. Then we were able to use the propagation of error formula to find out what is the variance in the value of q. And of course, by taking the square root, you can get the value in terms of the standard error or standard deviation of the error. Also, we refer to as standard error in q. If you again divide this by the value of the q and then multiply by 100, you get the percentage error, which was 0.55. And if you look at this next slide, the relationship between the various quantities given is in the form of product of quantities. That means P equal to m equal to P a into p divided by square root of t, it involves product of this, and therefore I can do what is called logarithmic differentiation, and that is shown here. So, what is logarithmic differentiation? You take the logarithms on both the sides, and maybe I can indicate it on the board. So, we have in this case m equal to a p by root t. So, I take logarithm of m, ln m equal to ln a plus ln p minus half ln t. Very simple, straightforward, and therefore, if I differentiate now, it gives m by dm by m equal to dA by a plus dP by p minus half dt by t. So, in fact, we can look at dm as sigma m, dA as sigma a, dP as sigma p, dt as sigma t, or dm by m as percent. If you multiply throughout by 100, for example, here, this will be the sigma m percent, this will be sigma a percent. While writing this step, I am going to use the error propagation formula. This will become square root of plus or minus, of course, sigma a percent whole squared plus sigma p percent whole squared plus half of this, half is coming because of the influence of this term is limited to that, sigma t percent whole squared. That is what we are trying to work out. Let me go back to the slide and indicate what has been done, and I have simply written down that formula here. After logarithmic differentiation, I get this, and what I can do is I can go next to the error propagation formula, and this is what I indicated on the board. Sigma m percent equal to square root of sigma a percent whole squared plus sigma p percent whole squared plus half of sigma t percent whole squared. That minus sign here is not going to make any difference, because I am taking the square of the quantity. You need not worry about the whether the influence coefficient is negative or positive, it is not going to matter. So, it will be simply given by square root of 0.1 squared, 0.2 squared plus half of 1 whole squared, which is 0.55%. In this case, because the relationship between the various quantities was in the form of a product, we are able to directly solve the problem using the percentage errors which are given, and therefore, it can be used only in such cases. In a more general case, the first method which I used must be used. Now, with this background, I am going to look at regression. What is regression? How are we going to perform a regression analysis? What is the method to be employed? These are the things which we are going to discuss in this part of the lecture. Regression basically involves or consists of determining the relationship that may exist between two measured quantities. They should have been measured, so two measured quantities. Or regression may be determining the relationship between any number of measured quantities. It may be one quantity, like in the previous case q equal to a p by root t is also a regression formula. A, p and t are measured, and the value of q is estimated, and the relationship is q equal to a p by root t. That is a formula, and that is also a regression formula for that particular problem. This relationship, what it does is helps us in presentation of data in a user friendly form. Either you can present the data in the form of a table and many graphs, and the person who is going to read through your report is going to look at all this and he is going to worry about how to use it, or if you yourself are able to make it in the form of a relationship, a simple relationship like what we gave earlier, m equal to AP by root T, or any such relationship, it is going to be much better for the person. So, what I have to do when I am reporting a regression formula is to tell the user what the formula is, that is the relationship is between a derived quantity and a certain measured quantities. Then I must also tell him what is the range of the values for which this particular formula is valid, or in the case of an experiment which is performed in the laboratory, you will know what are the values of the variables which appear in the or the measurements which you have done, what is the range of these measurements. For example, in the earlier case m equal to AP by root T, the pressure was given as I think 20, it may be valid for let us say between 5 and 25, then that is the range in which that formula is valid. Then T may be from, I had given a value of 4.84, maybe it is valid from 3 to 10. So, what I have to do is I have to give the relationship in the form of a regression equation, and also I have to give the values of the or the ranges of the various things going to the formula, and I also should, ideally speaking, tell the user what is the error I am going to make by using the formula, what is the plus or minus within the band in which it is going to give the value of the function. So, Q will be Q plus or minus some error margin, and the error margin also I must be able to give to the user. So, regression analysis consists of all these things. So, the very first step, however, in doing a regression analysis, to make a plot, you either make a one plot if it is only two variables y and x. If there is more than one variable, of course, one plot will not be able to give all the information. So, one may have to go for a number of plots. So, a plot or a set of plots is always useful before starting regression analysis. The plot will indicate what is the type of relationship I should expect between the variables. If it is only a single variable y and x, it may be either linear or a non-linear relationship. By making a plot, I will immediately come to the conclusion as to what is the best possible relationship that may exist between the two quantities. The plot will also indicate the nature of the relationship we should look for, that is whether it should be a simple relationship or maybe it is a complex relationship. It may involve several parameters. So, we will make some of these things clear as we go along. So, the relation may be either linear or non-linear, and I have just taken a few examples. The first example is a linear relationship. There is a parameter y, or there is a measured quantity y, there is another quantity x. These two are either measured, and we expect that these two quantities have some relationship between the two. Y and x are supposed to vary systematically with each other. In fact, you look for a regression or you look for an expression only when there is a systematic relationship between the two variables which you have measured, or two quantities which you have measured. If there is no relationship between y and x, if I make a plot, the plot will not show any definite relationship. The points will be scattered all over the diagram, and therefore, you can easily come to the conclusion that there is no relationship between these two. Suppose y varies and x varies independently, the two are not going to have any relationship, and therefore, you will not get a systematic relationship like what is shown here. In this case, y and x are showing some kind of a linear relationship. The data collected are shown by the black circles here, and the straight line is what I am expecting, and I will find out how to draw this straight line. That is the part, that is the basic idea about regression. The regression analysis first of all determines what is the regression equation or the relationship we should have. Secondly, it tells us what is that relationship, and then thirdly, it will also tell us what is the error incurred in using this relationship instead of the original data. So, let us look at the second type of relationship which you may have. Suppose I make a plot. In this case, I have taken log plot. Here I have log of x and here log of y. The logarithm may be either with respect to natural logarithm, with respect to base e, or you can take it with respect to 10, it does not matter. Suppose you make a plot on the log plot here, and if it appears as a straight line, so the original data can be converted to the logarithm of the respective quantities, and I can now look for a straight line relationship. So what is that relationship which will give rise to a straight line on a log sheet? We will see a little later. A third kind of thing which can happen is that the y and x are actually related in a nonlinear fashion. In this case, you can see x and y, I cannot linearize this relationship. This is possibly a polynomial, maybe a quadratic, maybe a cubic, whatever. So this cannot be approximated by a straight line. So what I am going to do is to find out what are all the situations where we can have a linear relationship. The regression could be a linear regression model. So the examples, I have shown two examples. The first example was where there was a linear relationship between y and x. Second one, when there was a linear relationship between logarithm of y and logarithm of x. And in fact, there is a third possibility, when you plot it on a semi-log paper, that means you plot x versus log y or y versus log x, then also you may get a straight line. So these are the three possibilities which exist for linear regression, and they are shown in the next slide. So in the first case, y equal to ax plus b plots as a straight line on a linear graph sheet. Then y equal to a x to the power of b plots as a straight line on a log graph, because you can take log y equal to log a plus b log x, and log y and log x are now linear in this particular thing. So you are going to replace x by log x, y by log y, I get a linear relationship. And the third one, when you have a semi-log plate graph sheet and the plot looks like a straight line, I will have y equal to a e to the power of bx, or it may be a 10 to the power of bx. I can use both. Okay, a e to the power of bx. You can see that log y is equal to log a plus bx. Logarithm of e to the power of bx is just simply bx. So you will have log y equal to a plus bx. And what is common between all these three cases? You have three cases here. What is common is that there are two parameters, a and b, a and b, a and b. So a straight line or a linear regression gives rise to a two parameter model. That means, let me just go to the board and explain to you this in slightly more detail. So we have a regression equation which is a relationship. If I am involved, I am talking about only two variables. Y is some function y of x, linear gives rise to two parameters a and b. A is the slope parameter. I am calling it the slope parameter because a itself may be a slope, or if I am using log, a may become something else. B is an intercept parameter. I am using the some terms slope parameter and intercept parameter in a general sense applicable to the three situations which are shown on the slide. One, x and y plot linearly on a normal graph sheet, x and y plot as a straight line on a log sheet, and the third case where it plots as a straight line on a semi-log sheet. So, A and B have different meanings depending on the particular case I am thinking of. The number of parameters is always 2. In all these 3 cases, we have 2 parameter model. And what is this? What does it mean in terms of the regression? We are finding 2, suppose the number of data is n, number of data is n, parameters is 2. So, you see the degree of freedom is equal to n minus p is equal to n minus 2. So, when I want to find out what is the likely error, I have to use n minus 2 in the denominator. For example, the standard error I will describe it a little later. This will be given by sigma I equal to 1 to n, the value of y I, which is the data which is given, minus y f I, y f stands for the fit or the regression line, this whole squared divided by n minus 2. Normally, we would have used n here. If the number of degrees of freedom is n minus p now, I am going to replace it by n minus 2. Therefore, I am calculating both a and b using the data. So, as I indicated earlier, 2 bits of information or 2 parameters have been obtained from the same set of data, and therefore, I have less information available now to calculate a third parameter. That is what the significance is. So, with this background, let me go back to the slide, and what I am trying to do is I am trying to see these 3 types of relationship. All of them are going to be linearized. That means that if I take plot appropriately, that means I am going to take logarithm both sides. In this case, I am going to take logarithm on only one side. Okay, semi log means I am going to plot in a different way, right. So, if I do that, the principle of least squares is going to be used for determining the relationship which I am looking for. So, what is the relationship I am looking for? General relationship now is a linear model. The relationship between y and x is a linear relationship or a straight line, and what I am going to do is I am going to look for a minimum value for the sum of the squares of the errors, the disparity between the values given by the linear relationship and the actual data which I have got as a measured set of data. So, let us look at the formula here. I want to minimize s squared. S squared is the sum of the squares given from sigma 1 to n, the number of data, yi minus yf whole square. Of course, yf is also yf is calculated for the value corresponding value of x. Therefore, it is equal to sigma 1 to n yi minus yf at the value of xi will be minus a xi plus b whole square. So, I have to minimize this value of a squared, because we have already seen when we are talking about the normal distribution of the errors and so on, that the sum of the squares must have the smallest value. That is when the value of the, in fact we found out that the mean value represents the best value for the quantity. There we were talking about a single quantity which is measured, but here we are talking about 2 related values y and x which are related, and I am now looking for the difference between the data y for a particular value of x and the value calculated by using the straight line relationship at the same value of x, and the difference gives you the difference between the two, and I am taking the square of this and summing over all the data points available from 1 to n, and I am trying to minimize this value. So, minimization requires that we evaluate 2 derivatives, dou s squared by dou a, this is one of the parameters. Second parameter dou a squared by dou b. Please notice that we are taking the derivative with respect to the parameter. X and y are all given values. the derivative is taken with respect to the two parameters a and b, and I have done here is to do that minus of 2 sigma 1 to n 2 into yi minus axi plus b multiplied by xi equal to 0, because I am taking with respect to derivative with respect to a yi minus yf whole squared, it will give you 2 into yi minus yf multiplied by the differentiation of this with respect to a will give you xi with a negative term. So, I have put the negative here. In fact, that negative is not going to play a role. Similarly, if I take with respect to b, I get the second equation sigma 1 to n 2 into yi minus axi plus b. With respect to b, this gives you just 1 with a negative sign, that is equal to 0. So, I have got two conditions for the minimization of the sum of squares, and these lead to two equations. What are the two equations? So, you just what I am doing is I am rewriting this in the form of an equation. So, it will be 2 into yi into xi, this 2 is common to all the terms. So, I can remove the 2. Similarly, here I do not have to keep the 2, negative also I can remove. Sigma 1 to n yi equal to, I am taking this to the other side, sigma 1 to n a times xi, a is a constant. So, I take it outside. So, you see that I write it as Ca into sigma xi squared plus b into sigma xi is equal to sigma xi yi. All this summation is over the values I equal to 1 to n, and I have not explicitly shown because it is understood from the symbol here. So, this is the first equation. The second equation is obtained from this equation. The first equation was from here, second equation from here, sigma yi, you can see that sigma yi equal to sigma xi into a plus n times b, because I am adding b again and again n times, it will be n times b. If you add the same constant again and again, n times, you are going to get n times b. So, what I have is the two normal equations which are shown here. The solution to these two equations is indicated in the next slide. We use a Kramer's rule, which is familiar to all of you. The constant a, or the parameter a, is obtained as the ratio of two determinants. The top one, we have sigma xi yi, sigma xi, sigma yi and n as the elements. The denominator is sigma xi squared, sigma xi and n. The denominator is the same for the two parameters, only the numerator is different, because we are going to replace the columns by the right hand column and then obtain the two constant quantities a and b. What I am going to do is I am going to use some definitions which are statistical in nature, and using these definitions I am going to rewrite the values of a and b by using the statistical parameters. So, this is shown in the next slide. The statistical parameters I am going to use to describe the data are given here. There are the means, two means are there. X bar is the mean of the values of xi. So, sigma xi by n, where n is the number of data points, it is the mean of the x's. Similarly, I have the mean y value, which is given by y bar equal to sigma yi by n, and I have got two variances, one corresponding to the variance with respect to x and the other one corresponding to variance with respect to y. So, the definition is very simple. We have already given this definition earlier. Sigma squared x or sigma x squared is equal to sigma xi squared by n minus x bar squared. This x bar is already calculated earlier or given here. Similarly, sigma y squared is the variance of the y's with respect to its own mean, and sigma yi squared divided by n minus y bar squared, y bar is from here. Third quantity which makes its appearance, if you go back to the normal equation, you will see that we had product like sigma xi yi. This product or the summation of the product of two quantities is called the covariance, and the covariance is nothing but an indication between the variability or the influence of yi on xi or in xi or yi. So, the two are going to have some mutual understanding with each other, and therefore the variation in the two are related, and therefore the covariance tells me what is the relationship between xi and yi. In fact, we will talk more about it a little later on. So sigma xy is sigma xi yi, the summation of the products of x and y divided by n minus x bar y bar, which is from here. X bar y bar is from here. So the two quantities a and b, which are given in terms of the determinant, the ratio of two determinants here and the ratio of the other two determinants here, these can be recast in a form which involves the quantities defined here, these x bar, y bar, sigma x squared, sigma y squared and sigma xy, and the intermediate steps can be supplied by you. You can work it out, and I will leave it as an exercise for you to do it. And the slope of the regression line a equal to, we can show that it is equal to sigma xy, the covariance, divided by the variance of the x's, or sigma x squared. Similarly, in fact, if we go back to the normal equation, we can see that sigma xi, what is given here, is nothing but nx bar. Sigma yy is nothing but n y bar, and n is here. So if I cancel all the n's, or if I divide this equation by n, I will get x bar times a plus b is equal to y bar. That means y equal to ax plus b is the straight line, and y bar is equal to ax bar plus b. That means that the point x bar y bar is a point which the regression line passes through the point x bar y bar. So the intercept can be obtained by noticing, as we just did now, that y bar and x bar is a point on the straight line or the regression line. So we can say that b equal to y bar minus ax bar, and a is already obtained here at the slope given by sigma xy divided by sigma x squared. So the two fit parameters a and b have been obtained by a simple procedure which involves the statistical parameter sigma xy, which is called the covariance, then the statistical parameter variance of the x's, which is called the sigma x squared, and the mean values of x here and the y here. So with these 4 statistical parameters, we are able to get the regression coefficients. So we have now a way of calculating the parameters a and b, the slope parameter and the intercept parameter, and now we would like to ask the question as to whether this particular straight line we have found, does it represent the data well or not well. So the question we are going to ask is about the quality of the fit, which is also referred to as the goodness of the fit. The question is, how well does the regression line represent the data. So in order to look at that, in order to do that, I must look for some internal consistency or some parameter which is internal to this procedure, which is going to indicate to me whether the fit is good or not good. So for this, what I am going to do is I am going to look at an alternate way of representing the data. What is this alternate way? Let us look at that. So alternate way of representing the data. Let us look at that, and that is, I took y is equal to ax plus b. I will call this the first line. I could also have taken x equal to some a dash y plus b dash. I will call this second line. So what I did earlier was to assume that y and x were linearly related in the form y equal to ax plus b, where A was the slope of that line, B was the intercept. Instead of that, why not take x as a function of y and y in the form x equal to a prime y by place prime. Of course, I can represent this slightly differently by solving for y equal to, so I will retain it here, send this b prime to the other side, 1 over a prime times x minus b prime divided by a prime. So, I can say this is something like a x plus b, where a is this quantity, 1 over a dash is a, and this minus b dash by a dash is your b. All right. So, what I am saying is, it is possible to relate the x and y in a different form by writing x equal to a prime plus y, a prime y plus b prime, which is equivalent to writing in the form y equal to capital A x plus b, where a is 1 over a prime. So, we will just write it here, a equal to 1 over a prime, and this b is minus b prime by a prime. That means that if I perform the regression using this line, after performing the regression, I will obtain a prime and b prime exactly similar to the method which we used in the case of the first line, and then I will replace it in this form by representing it as a straight line, y equal to some capital A x plus b, and the slope of that line is 1 over a prime, the intercept of that line is minus b prime by a prime. So, the method used for a prime and b prime is exactly similar to a and b, and therefore, we can easily obtain capital A and capital B as a slope of a second line and intercept of a second line. Suppose I compare the slopes of the two lines. So, if the slopes of the two lines are compared, so we compare the slopes of the two lines. And if the slopes of the two lines are close to each other, we say that the correlation is good. If the two slopes which we calculated come very different, obviously the fit is not good. So, we can only say whether the fit is good or bad by comparing the two slopes or the slopes of the two regression lines, and in fact, I can take the ratio of these two slopes and relate it to the goodness of the fit. So, we will say that the ratio of the slopes, if I calculate the ratio of the slopes, if it comes close to 1, it means that the regression is good. If it comes very small, then the regression is not good. So, ratio of the slopes is a measure of the goodness of the fit. So, with this background, what I will do is I will show you how the second line is obtained, and we can look at the two slopes and introduce a parameter which is going to describe whether the correlation is good or bad. So, second regression line I have indicated here, just as I showed on the board, x equal to a prime y plus b prime, and now we remember what we did for obtaining a and b. A similar procedure gives you a prime equal to sigma xy divided by sigma y squared, b prime equal to x bar minus a prime y bar. So, b prime and a prime are obtained by using the statistical parameters, and then the second line is given by y prime equal to 1 over a prime x minus b prime by a prime, and therefore, you can see that the ratio of these two slopes, slope of the first regression line divided by slope of the second regression line, this will be nothing but the product of a and a prime, because 1 over a prime was the slope of the second line, a was the slope of the first line, Therefore, I have to take the product of these two, that will give you sigma xy squared divided by sigma x squared sigma y squared, and therefore, this we call as the R squared or the correlation coefficient, or we also call it the coefficient of correlation. R is the coefficient of correlation. We refer to this as the R squared parameter, and that is given by sigma x y whole squared divided by sigma x squared sigma y squared, or sometimes we use the symbol rho equal to plus or minus sigma x y by sigma x sigma y. This plus or minus will come into the picture, because if you look at the numerator is a product of x and y. Sigma x y we have defined earlier is the covariance. Covariance is nothing but sigma xi yi divided by n minus x bar y bar. This may be either negative or positive. It will be negative if x, as x increases, y decreases, then it will be negative. If x and y increase at the same time, or they are behave alike, then the slope, the covariance will be positive. So, if the regression may give either a negative correlation or positive correlation, negative 1 minus 1 will be equally good, plus 1 is equally good. If the value is far away from either plus 1 or minus 1, we can say that the correlation is not good, or the relationship is not a good relationship. So, I have explained it here. The sign of the correlation coefficient is of course determined by the sign of the covariance, and the correlation is said to be perfect if rho equal to plus or minus 1. I think I have to go back to the previous one. If rho equal to plus or minus 1, the correlation is good. The correlation is very poor if rho is very close to 0, and in fact in practice we should get a value of rho greater than 0.5 or less than minus 0.5. It should not be less than these two. It should not be less than 0.5, or it should not lie between 0.5 and minus 0.5. Anything more than 0.5, there is some likelihood of a correlation. Of course, closer it is to plus 1 or closer it is to minus 1, the correlation is going to be the best you can think of. So, with this, let us take an example. Not working. Which indicates how this procedure is to be done. So, I am taking a data which is very simple, which is expected to show a behavior of the form y equal to ax plus b, and I want to determine the fit parameters by linear regression, the procedure which we have just now given. The x and y values are given in the tabular form. The first row gives the x values 0.9, 2.3, 3.3, 4.5, 5.7 and 6.7, and the y values are given in the second row 1.1, 1.6, 2.6, 3.2, 4 and 5, and we can immediately see that x is increasing, y is also increasing. Therefore, we expect the covariance to be positive. That means that the slope is going to be positive. Y equal to ax plus b, a is a positive quantity. So, in order to do this regression, it is necessary to put the whole thing in the form of a table, so that all the statistical parameters can be obtained. So, the data number 1 to 6, then x's are given in the first column, y values in the second column. Then if you remember, the statistical parameters require the calculation of sigma x squared, sigma y squared and sigma xy. Therefore, x squared, y squared and xy are calculated and put in the tabular form. Then I sum all the columns up to the number of data we have. So, this is 23.4 is sigma x, sigma y is 17.5 and sigma x squared, sigma y squared and sigma xy. So, you can see that the column sums are given, and the column means can be calculated by simply taking this number dividing by the number of data points. That is also done here. So, once we have got the column sum and the column mean, I can calculate sigma x squared, sigma y squared. This will be nothing but the column mean here 19.1033 minus the square of the column mean here 3.9 squared. So, that gives you this, and similarly sigma y squared, and in fact I can calculate the slope of the fit. This is covariance divided by sigma x squared. covariance is calculated by using this quantity 13.9917 minus x bar y bar and then dividing it by sigma x squared, and you will see that it is 0.6721 and the intercept is 0.2955. So, now I can compare the fit or the regression line with the data given and find out whether the fit is good or bad. So, the first one I can make the table like this, x and y, these are the given data and this is the fit line which is calculated using the regression analysis we have done earlier, and you see that these values are close to the values of the y. The y's in the third column are close to the values and therefore, the fit appears to be good, and in order to confirm further I can calculate the correlation coefficient by using the formula which we gave earlier, this 2.6167 divided by square root of sigma x squared sigma y squared, this gives you 0.992. The correlation coefficient is 0.992, very close to 1, and therefore, we expect the fit to be very good. And in fact, I can show the comparison also in the form of a plot, and the plot also indicates that the dark circles here and the line are close to each other, and therefore, we expect the comparison to be good or the correlation to be good. We will stop here in this lecture. In the next lecture, we will continue with some more discussion regarding the both linear and nonlinear fit, take one or two examples and then move on to the next topic. Thank you.